Alright, so hello everyone. Today Brett, Bays, and I are going to be talking about humps, and we aren't talking about your mothers.
That's right, Will. We're talking about critical flow and applying Bernoulli's equation to flow over humps.
We want to demonstrate Bernoulli's principle with a fixed width channel and humps of varying shapes and sizes. These humps are typically used to change flow speed, but you could reverse this by using only the hump and a ruler to measure the rate of flow.
Now, we're modeling the flow of the water as a two-dimensional steady flow through a channel as seen in front of us. Now, this channel also has an underwater hump in the middle that covers the width of the channel. In order to see if Bernoulli's equation applies, we've gathered some equations to aid us in the math.
Oh my God!
Something that's important to keep in mind about flow is its criticality. The Froude number, whose equation is seen here, describes the ratio between inertial and gravitational forces in the flow.
When the height of the hump reaches critical height, subcritical flow upstream is compared to supercritical flow downstream at the top of the hump where the Froude's number equals 1.
For testing, we decided to build a river channel that has a detachable hump in the middle, as stated before. The flow rate was measured at the faucet, and the velocity upstream was calculated using the conservation of mass equation. This velocity was compared to the velocity calculated using the change in height of the flow over the hump, the height of the flow upstream, and the height of the hump.
Here's our results. You'll see here that the velocity calculated from the flow heights is pretty close to the velocity calculated using the measured flow rate. You'll also notice that the error increases with the hump height. But one other thing to note is that the height of the flow of the water over the hump is the same regardless of the height or shape of the hump. This critical height is a function of the Froude number of the flow upstream. Knowing that, we found that the critical height is around 0.73 inches. We also added another hump that was below this critical height. And here you can see how the hump height is below the critical height, and so the flow is subcritical.
Thanks for that, Will. When the hump reaches a certain height, we see damming action, where the height upstream is higher than downstream. When the hump height is below the critical height, then we see the water return to its upstream height downstream. This critical hump height is a function of the actual hump height, but not the hump shape, which is why you see here that humps of different heights and shapes that are above the critical hump height still have the same critical flow height above them.
The best way to improve this project is to have more accurate height measurements and also build something more like this. Post-grad students from the Irrigation and Hydraulics Department at the University of Cairo built a much larger and more accurate flume to measure how different hump conditions affect flow.